unipolar properties in near horizon space-time, we have no idea how currents can be generated within the black hole magnetosphere at this point. So the point of this talk is to motivate the microphysics that can drive currents from a black hole magnetosphere. In particular, what is the ergospheric physics that can drive currents? And what we'll find out is that it's the frame dragging effects within the ergosphere that allows the gravitational field to drive a colloidal current system. It makes a dynamo, essentially, for the toroidal magnetic field. And we want to understand at a very fundamental level what the microscopic forces that drive the macroscopic currents are. Without that, if we just write down solutions, we don't know if they're physical or not. The microphysics of current generation has to be within our solutions, or we don't have a solution at all, we just have mathematics. So, going back, I gave a lot of examples for those of you who were here for the last talk of how a laboratory unipolar inductor works, a rotating wheel with a magnetic field threading it. And if you attach it to leads, it drives a current. And the reason why it drove a current was because there was a slight unbalance of the EMF by the electromotive force by the electrostatic field. You always had an unbalanced EMF, and that's what drives currents. And furthermore, the rotational inertia of the Faraday wheel is converted into Poynting flux, and we attached it to a plasma-filled waveguide, which is the analogy to the black hole magnetosphere. So we want to find some kind of unbalanced EMF that can exist in the magnetosphere that can actually drive currents. And what we will find is there's a rotationally induced EMF from frame dragging, just like in the unipolar inductor, the Faraday wheel. And we'll also see that relativistic rotational inertia that's been imparted to the plasma by pure general relativistic effects, will be converted to Poynting flux, just like in the Faraday wheel. No, that doesn't look right. No, that's not this. Well. So the basic model that I'm going to consider, lost my little pointer here, and these are just thought problems. This doesn't necessarily represent a real physical situation. We're going to do highly idealized flows to understand what the physics is in the ergosphere that can drive currents. And the presumption is that the essential physics is the same in more realistic flows as well. So we have a particle creation zone, an idea that was introduced by Stirl-Finney. We're going to consider pair plasma creation. It doesn't really matter for this case, but eventually I will introduce a pair plasma creation model. And we have two winds. One ingoing wind that's going to go into the ergosphere, not necessarily through the event horizon, but into the ergosphere, and another one that goes out to asymptotic infinity. And in each wind, there are going to be constants of motion in the wind. KE is the energy flux, KL is angular momentum flux, K is the mass flux, that we have the entropy and the field line angular velocity. So it's a paired wind problem. It's got an accretion wind and an outgoing wind that can go off to infinity. Oops. So what the physics is going to be, and I'll mention this term a few times. In the United States, we have something that people play called the tug of war. You get two teams and a rope, and both teams pull against each other. Well, the plasma near the black hole and the plasma far away are in a torsional tug of war in these magnetic flux tubes. The plasma far away does not want to rotate. The plasma near the hole wants to rotate, and that twists up the magnetic field lines. And that twisted magnetic field, just electromagnetically, is an angular momentum flux along the field lines away from the hole. And so that's the essence. I'll describe a lot of physics, but that's the essence of it. You have two regions that are competing to establish the rotation of these field lines, and they twist them up. Now we have these different constants of motion, which I mentioned, and in a warm, magnetically dominated wind, where the field's very strong, fortunately, we reduced these 5 basically to 2. It's warm, but so the entropy isn't that important. It's not relativistically hot. And all of these terms are equivalent in each one of these lines, and that's a key thing. And I'll go back and forth with different terms, but they all mean the same thing. We can talk about the toroidal magnetic field. That's like in wind theory, R B phi, B phi being the azimuthal component, that's a general relativistic analog. We have KL, the angular momentum flux, totally equivalent to the toroidal magnetic field in a magnetically dominated wind. We have the field line current, a line current flow, colloidal current. Again, due to Ampere's law, that's the same as the toroidal magnetic field. And we have the angular momentum flux in the field, which is the angular momentum flux for the wind. The other constant of motion can be expressed either way as the voltage drop across the field line, the field line angular velocity, the energy flux, or the Goldreich-Julian charge density from pulsar physics, who I've mentioned a few times, some other people have mentioned it, the amount of charge it takes to short out the electric field and proper electric field in the magnetosphere. The Goldreich-Julian charge density is equivalent to the voltage drop, because those are the charges that are separated to make the electric field of the voltage drop, and also the Poynting flux. All these are just absolutely equivalent. And here's an expression, for instance, that shows what the voltage drop is in terms of the field line angular velocity and the amount of magnetic flux that's in an azimuthal flux tube. You can think of them as a flux tube azimuthally symmetric and very thin. And one of the interesting aspects of this is that the Goldreich-Julian charge density is advected with the wind. It goes off to infinity, so it always constantly has to be replenished, and that's the role of the dynamo in a wind problem. So we want to find a way of causally determining these constants of motion in the wind. We know there's no unipolar inductor with the horizon, or near the horizon. We know that can't causally determine anything. And first of all, it was shown by Bishok and Dvorak that axisymmetric electromagnetic fields do not torque black holes, so we have to introduce plasma to get energy out of the black hole. So we look at all the possible modes of communication within the system to determine the causal structure. And again, we are looking at the axisymmetric case because that's probably the most likely case astrophysically and should be a good first-order approximation. We have the gravitational field, we have light waves that could possibly carry information, MHD waves. We can introduce dissipation within the system, and we can have MHD waves that are modified by small dissipation. Okay. I put it down because it was feedbacking all the time, but we'll see what happens. And the other thing is we have a lot of dissipation in the system, and we can have plasma waves in a highly dissipated medium. So we want to look at the role all these plasma waves can have in determining the constants of motion in a black hole-driven wind. So first of all, let's look at the gravitational field. Well, the gravitational field, in spite of some claims to the contrary, only couples to mass energy, not electric charge. So gravity itself cannot drive a current system or establish Goldreich-Julian charge separation for the global potential or equivalent. There has to be an intermediate step where the gravity couples to some massively electric charges, and those can be communicated upstream to the plasma source, not going wind. Stand up. What? Yeah, I noticed that too. It's coming from over there, right, when I was sitting back there? Does it help when I put it down lower? Better? This didn't help when it was down here? Oh, smoke? Okay, we'll see. You adjusted something there? Okay, we'll see if there's some improvement. Did I make it better or worse? I can hear that one here. I think we have the technical experts in action right now. Okay, is this any improvement? How about now? Is this better? Okay. So the point of currents, there needs to be an intermediate mass. Good? How about now? Is this an improvement? Okay. Well, thanks for pointing that out and not letting this just go on indefinitely. So gravity can't drive the currents. It can only couple to the mass energy of the plasma. Once it moves the plasma, couples to it, there has to be an intermediate step where the electric charge can radiate information. Electric charge can radiate information upstream to the outgoing wind in the plasma source. We can also look at the role of light waves. And we killed two birds with one stone here because in the highly dissipative plasma waves, the only propagating waves that couple to electric charge are essentially light waves as well. So we can look at both of these at the same time. For an astrophysical black hole of, say, like 10 to the 8 solar masses, we expect the field to rotate like 10 to the minus 4 hertz. So this angular velocity is much less than the plasma frequency of the magnetosphere. And so the relevant light waves that we need to establish from our dynamo to establish the field line angular velocity omega f have to be on the order of omega f. And so they're all in the reactive range. And so they do not propagate in the magnetosphere. So light waves cannot be used to determine, nor can waves in a highly dissipated plasma be used to determine the voltage drop across the field lines or the field line angular velocity equivalently. So we look at MHD waves, and MHD waves is modified by dissipation as the only possible source of communication that can be used to determine the field line angular velocity, equivalently the voltage drop, as well as the toroidal magnetic field, or equivalently the current along the magnetic field lines. And remember, going back to the analogy of the unipolar inductor that I stressed for the whole talk, is that the Faraday wheel used MHD waves, Alfvén waves, to determine these quantities in the plasma flow waveguide. So this is totally analogous to that situation. So this is the causal structure of any dynamo of a black hole. It has to be this way. There's no other causality that can work. Gravity couples to mass energy, not electric charge. Plasma then can be dragged across the magnetic field lines by black hole gravity. This creates a Lorentz force that's opposite for each species of charge. The resulting current that this creates is the final coupling. It's through J cross B force and Ampere's law. That's how the black hole ends up coupling to the magnetic field for this intermediate step. And the intermediate step is essentially a plasma wave interaction. And so this, of all the things I'm going to say in any of these talks, this is the physics right here. This is the view graph that matters. And I'll go into the specifics of it, but there's no mystery as to how a black hole drives current. It's all physics that we're used to seeing. What? What was it? Yes, that's right.
There's no electric current.
No, they both move together, but Q is opposite. So the Lorentz force is opposite. V cross B is the same. QV cross B is opposite, and that drives the current. It's a black hole in a strong magnetic field. It's the strongest thing in the universe. So we'll take a look at it. You have two tremendously powerful forces at odds. You're talking about other questions. This is, I said, this is a thought problem. And a lot of the questions you're asking are related to other talks. But we're assuming there's a magnetic field around the black hole. And it is very plausible, but we can talk about why it's plausible, and lots of people look at it. In general, what we're assuming here is we have, and this is the most general situation, is we have a Kerr-Newman black hole that creates a colloidal flux, as well as a surrounding accretion disk that generates, it's like in the other problems I talked about, that has an azimuthal current that also generates a colloidal flux. Wald found out many years ago, argued that the colloidal flux from the two contributions have to be on the same order of magnitude for rapidly rotating holes. So you always have to have a Kerr-Newman hole. It's never a Kerr hole. The hole has to attain a charge in its minimum energy configuration. So there's two components, but they're both axisymmetric. There's a small charge, just like on the pulsar's charge. It's the same charge that's in the pulsar, a neutron star in the pulsar. It's totally identical. But that is not necessary for the physics I'm telling you to work. It's just a fact. You ask for more details, and it's a fact of what the colloidal field structure is like. It's an inescapable fact, and I was just trying to give you a little extra information there. But don't concentrate on that detail because it's not really what this talk is about. So we have the magnetic field threading the hole, and this talk is about a very interesting problem. Let me rephrase it. No one knows how the black hole magnetosphere, ergosphere, can actually drive currents. This is an open topic. And so that's really the emphasis of this, to understand that microphysics, not all these other types of problems. So first of all, let's see, we talked about the gravitational field dragging plasma across the magnetic field lines is the way the currents are going to be generated. First, let's look at radial gravity. Actually, I think I lost a view graph here in that discussion about Kerr-Newman black holes. We still want to understand this unbalanced EMF, and we have two types of gravity. We've got radial gravity that's dominant near the horizon, and we have the force of frame dragging that can dominate physics way out at the stationary limit. So we want to look at the effects of both types of gravity here. So first of all, radial gravity. It'll generate a colloidal velocity. It'll drag the field in the plasma basically radially. So first of all, V cross B colloidal force is generated at J phi, and that's neutral current. And that's the current that's associated with the Grad-Schaffner equation, the determination of the colloidal field, not the toroidal field. Then to first order, V cross B toroidal 0, because we're trying to generate a current out of an axisymmetric situation, putting plasma on. So to first order, that's 0, but in the next few, I can talk what can possibly happen to second order if some perturbation makes the vacuum toroidal field non-zero, the plasma perturbs it. But just in a general concept, that causality dictates that by the time radial gravity dominates, the flows are going to be moving in supermagnetosonically, so it's going to be out of causal contact anyway. So that's a good thing to note. So let's look at second order with radial gravity. The idea is it possible some perturbation in the toroidal magnetic field can be amplified by radial gravity, and then that be radiated upstream to the outgoing wind and plasma source. We can't rule, until we discuss this, we can't rule out radial gravity yet as the source of the dynamo. So for a positive colloidal field in the northern hemisphere, the energy extracting condition, angular momentum extracting condition, is the toroidal field less than 0. Radial gravity pulls the plasma inward, basically will make a radial current across the toroidal magnetic field, and that J cross B toroidal force will drive a J theta poleward, and if you do Ampere's law, that will actually switch off the toroidal magnetic field. So this is a quenching type force. It damps the instability. So radial gravity through J cross B toroidal forces can never generate a toroidal field that grows upstream, the kind of toroidal field we're looking for in an outgoing wind. On the other hand, frame dragging naturally produces this. Frame dragging will pull plasma across the colloidal magnetic field in the positive phi direction, the direction the black hole wants to rotate. That's the interesting aspect of the Kerr geometry. It makes everything rotate with the hole. This V phi cross B colloidal force creates I call it J perpendicular, a current across the magnetic field. I also call this J2. I can define directions 1 along the field and 2 perpendicular. But this is directed equatorward. And this toroidal field is less than 0 upstream by Ampere's law. And it can be radiated upstream as long as it flows submagnetosonic. Once the flow's gone supermagnetosonic, the flow upstream doesn't know about this. But this is the exact same physics that's in the Faraday wheel. It's a V phi cross B colloidal EMF, just like in the Faraday wheel. And the current generation should occur in the outer ergosphere, where frame dragging is still strong, yet the flow is not moving inward so fast that it's supermagnetosonic, so it can be radiated upstream. So we want to get into the details of this frame dragging and this torsional tug-of-war I was talking about. Oh man, that's bad. Let's see. Oh, it doesn't matter because you have the view graphs there, right? It doesn't make any difference. I don't have to sweat this. So even though you can't read a word of what's up there, if you glance at the view graphs, we have, for any plasma velocity omega p, it's bounded by a minimum and maximum angular velocity. This is the angular velocity of the plasma seen from asymptotic infinity. Here's expressions for omega minimum, omega max. The omega minimum part is a very interesting part of the curve geometry. It's the frame dragging aspect. Here we express it in terms of the angular momentum of the ZAMOs, a frame that, unfortunately, I'm not going to have time to reintroduce in this talk, but it's just an orthonormal frame with constant radius. And here's the lapse function. Again, this goes to 0 at the horizon. So important I will reintroduce it, and represents a gravitational redshift of the ZAMO frames. And so note that when the plasma angular velocity equals omega minimum, in the ZAMO frames, the plasma is rotating backwards at this rotating backwards at the speed of light. That's beta phi's in the ZAMO frames. And at the horizon, omega minimum goes to omega h. Here we have the definition of the stationary limit RS. Omega minimum goes to 0. And everywhere within the ergosphere, omega minimum is bigger than 0. So we'll use these facts to describe this torsional tug-of-war, which is in this picture right here. How am I going to do this? Oh. It's too torturous for people to read. I don't have a choice. So this again is, which to choose? This, what do I do, this thing? Oh, I can put it this way and then, oh, okay, thanks. And then zoom out. And still, it's good to have your view graph with you because the writing's going to get very small. So imagine a flux tube that extends off far away from the hole and goes into the ergosphere. And we have frozen in plasma represented by these Lamore orbits. So then these helical trajectories. Far away, so here's the colloidal magnetic fields in this direction and the hole is rotating around this axis. Far away, in order to keep the azimuthal velocity bounded, the angular velocity of the plasma has to go to 0 far away. You expect some kind of divergence in any flow. Even if it's minor, far away, the angular velocity is going to be very small. Secondly, for perfect MHD, we have the voltage drop is equal to this constant across the field lines, where delta phi is the amount of flux in the azimuthally symmetric flux tube. And so omega f is a constant along the flux tube in perfect MHD. If you just so perfect MHD has this interesting property that omega f is a constant.
The field line angular velocity in the flux tube. Now, inside the ergosphere, we have omega p has to be bigger than 0 because it has to be bigger than omega minimum. That's the definition of the ergosphere. It has to actually increase to the angular velocity of the horizon.
So deep in the ergosphere, omega p is going to be in the order of omega h, angular velocity of the horizon, maybe at 2.
Once it gets close, we see we have a big problem. There's no value, right?
A semi-rigid but untwisted flux tube of the field line angular with plasma at asymptotic infinity, which doesn't want to co-rotate, and the plasma is deep in the ergosphere. The only way that this problem can be resolved is if the field gets twisted, and the plasma in the ergosphere can rotate, be able to slide along the magnetic field, co-rotate, avoid this co-rotating with the field. And this bent toroidal field that allows you to do this
is precisely equivalent to this equation here at the bottom to an angular momentum flux, a conserved angular momentum flux in the flux tube. So that's how the torsional tug-of-war generates angular momentum flux, and it's purely electromagnetic angular momentum flux. So that's the last picture we're going to see for a while, and we'll start analyzing the ingoing wind. And what I found very useful was introducing a new basis I call the rotated ZAMO basis. The ZAMOs only have two dynamical components, phi and t. The r theta plane is non-dynamical, so we can rotate any way we want in the r theta plane and still have a ZAMO observer, zero angular momentum observer. And so what I do is I pick the one direction to be along the colloidal magnetic field and the two directions to be perpendicular to it. And I can express all derivatives in terms of ZAMO derivatives this way. And so I reformulate all the equations in this frame, and it makes them very easy. Now, first of all, I define a co-rotating frame of the field. The velocity of that be u bar, F is the Maxwell tensor. And so here's the azimuthal velocity solving this equation of the field. Implicitly, what this expression is, it's relating the azimuthal velocity of the field to the angular velocity as seen at infinity, this omega f. So we have an implicit definition of omega f in this formula. So once we have this azimuthal velocity in the Zamo frames, we can always get the angular velocity in the stationary frames. Now notice that for field lines that thread the horizon, alpha goes to 0, and so the field angular velocity is going to go to minus infinity, and similarly for an outgoing one, it goes to plus infinity. But this is a very important point. For field lines that thread the equatorial plane, the lapse function never goes to 0, and so you don't have to have the field rotating at minus the speed of light anywhere on flux tubes that go through the ergosphere and also the equatorial plane. An interesting case that we're going to look at for this very reason. We also have this concept of a light cylinder. Since beta phi approaches without bound on the inward flow, there has to be a light cylinder where beta phi equals -1 in the ingoing flow. For omega f bigger than 0, this is always inside the ergosphere. Similarly, we have an outer light cylinder. But for flux tubes that thread the equatorial plane in the ergosphere, they do not necessarily have to have a light cylinder. And that allows them to define the physics on those field lines much easier. A very important concept of these ingoing winds is the toroidal magnetic field. This is the toroidal magnetic field in the Zamo frames. Here we have the azimuthal velocity of the plasma, and here we have the poloidal velocity. What's more useful and for conservation equations is the Boyer-Lindquist toroidal field related to the Maxwell tensor and Boyer-Lindquist coordinates, B toroidal. I've already introduced it but never explicitly show what it was. It's useful because there are two conserved quantities in a magnetically dominated wind, essentially, the redshifted Poynting flux and the redshifted angular momentum that depend explicitly on B toroidal. So we have constants of these winds in a flux tube. We have the mass flux, and we have the specific energy and angular momentum per unit magnetic flux. And these pieces, the M and the W, are the specific mechanical angular momentum and energy. This is the mu is the specific enthalpy. These are the view graphs, if you want to get them. That's the first top. You got the second one there, and there's the first one, the ergosphere-driven winds. So we're about halfway through. So the specific enthalpy is this mu. The reason I mention it is because a lot of these symbols are hard to read up here, but easier on the paper. Notice that I've defined this mechanical angular momentum with a minus sign relative to the way most people do. It's from an earlier paper of Unruh that I started many years ago in this subject with, and he defines it opposite of everyone else in that paper. So minus m is actually the specific mechanical angular momentum. We can get from u dot u equals -1, we get some algebraic relations for the velocity of the flow in the toroidal magnetic field. M is the pure Mach number, defined in terms of the pure Alfvén speed. And notice they're all singular when m squared equals 1 minus the field line azimuthal velocity squared. That's significant because it's the intermediate speed or Alfvén point of the flow. And even though there are three speeds of MHD waves, and we're going to start talking about MHD waves exclusively from here on out, now that we've established that MHD waves are the key causal mechanism. These U1 should be lowercase over here. That's the poloidal velocity. This is for the fast and the slow mode. There's three modes. A lot of you don't know that much about MHD waves, but the sound wave couples to the two polarizations of the light wave. And so you get three modes in a plasma. The slow wave is almost purely longitudinal. The Alfvén wave, which is the very interesting one for torsional stresses, is purely transverse. And the fast wave can be, depending on its angle of propagation, can be in any balance of longitudinal and transverse. Here's one example of the usefulness of the Zamo frames, is that this Maxwell invariant takes on a very simple form. So this is the expression for the fast and the slow speeds. This is for the intermediate or Alfvén speed. And we get another expression for the fast speed. Just to let you know that we can define these expressions, not that you need to know what they are. If you look at these expressions, all inflows cross the Alfvén point before reaching the inner light cylinder. That's the point in not necessarily having inner light cylinder and field lines that go through the equator. That's what makes them important. Because the ZAMO colloidal velocity increases negatively without bound near the horizon, and the fast speed is made of proper frame quantities, all flows have to go through the fast point, go super fast before reaching the horizon. Yet, for flows that go down towards the equatorial plane, they need not pass through the faster or alpha and critical points of the flow. And these are critical points in the field-aligned colloidal direction momentum equation. So the important part of this is that causal contact can exist between plasma and equatorial disk, and some kind of equatorial disk, and the outgoing wind and plasma source. Equatorial disk conceivably in the ergosphere launch alphane waves out, which we had in the Faraday wheel attached to the plasma-filled waveguide. I'm going to skip the next view graph to save space. Make one very small comment on the outgoing wind, something that's useful to know. They've been looked at originally by Keno, Fujimura, and Akamoto, unraveled the critical point structure of outgoing relativistic winds. Kamenzind has done a lot since that, since '86, many articles. We're going to assume the Michael minimum torque solution, which has the flow going the speed of light at infinity. You get a simple expression for the toroidal field at infinity, where phi is the total flux enclosed by a magnetic flux tube. A potentially confusing concept. Even looking at it sideways, well, we still can't tell. This is just the arbitrary field shape. Here's the hole, here's an accretion disk. This is an azimuthal flux tube with flux delta phi. The flux enclosed in the flux tube is this flux inside of the azimuthal flux tube. It's a concept that confuses people a lot. So there's two different fluxes that we're going to be talking about. The flux totally enclosed by the flux tube and the flux of the flux tube. So in order to understand the coupling in the ergosphere to winds, we're going to make a simplified ergospheric disk model. Remember, there's nothing special about the horizon. There was no unipolar inductor effects near the horizon, so there's no reason to consider field lines that go through the horizon to understand the coupling to the plasma in the ergosphere. The same effect should occur on field lines that go through the ergosphere, then through the equatorial plane, and therefore not the horizon. And those are going to be easier to understand. So this is you get tremendous insight on the physics from doing this, because you don't have the open-ended problem of going into the horizon. So we're going to make this really simplified paired wind model, and hopefully we're going to expose all the microphysics we talked about, and plus expose some nuances of this interaction that we didn't know about before. So the basic model, I should be getting good at this, this is just awful. It's going to look like this. We have a black hole, an accretion disk, which is the source of the magnetic field. We have a lot of flux through this ergospheric disk. We have pair plasma created up here. Again, it's just a thought problem, too, this wonderfully ordered magnetic field. But note the magnetic flux is less through the horizon. That's intentional. So the important thing about looking at this problem is that this will extract the rotational energy of the hole, this ergospheric disk. It's unlike an accretion disk-driven wind, which just extracts the rotational energy of the accreting plasma. And so that's what we want. We want to understand how the black hole's energy can be lost. And I note that one possible relevance of this problem is that Bicak and Janis found that as the angular velocity of the hole goes to M, the astrophysically interesting case, you get flux suppression through the horizon. So it may be very interesting to look at field lines that don't go through the horizon, because those may be the only ones you have in an astrophysical problem. Now, in order to understand the energetics of this problem, we introduced the idea of negative energy states of plasma in the ergosphere. This is the key to coupling to the horizon, coupling to the hole. Again, here's the specific mechanical angular momentum with an extra minus sign. Minus m is really the specific angular momentum. Here's the specific redshifted mechanical energy. And from these expressions, I've expanded them out here, that if the plasma rotates backwards and near the speed of light in the ergosphere, the angular momentum minus m, going to work backwards, is negative, as seen from infinity. plus the energy is negative as seen from infinity. Locally, in any local physical frame, it appears to be positive. But it's negative as seen to be infinity. In fact, very highly negative, because for beta phi equals to -1, this U0 is very large. So you can get very strong interactions here. Just to motivate the idea of a flow towards the equator, there's two forces of gravity at work here in the flux tubes. There's a regular radial gravity towards the hole, and there's also, in the ZAMO frames you can write out, there's also a force of gravity from this Christoffel symbol towards the equatorial plane from both sides. That allows you to always accrete towards the equatorial plane. If you look at next order in this, is if you overshot the equatorial plane, there's going to be a restoring force from the Riemann curvature. And plus, from the symmetry of the problem, the way we propose it, you have flows coming from opposite sides. The only steady state to this flow is clearly going to be a disk. And we find when we study this disk that a slow switch-off shock will bound both top and bottom of the disk, and this will break the flow down to the slow velocities in the disk atmosphere. And the inflow we find from looking at the Rankine-Hugoniot equations is at the alphane speed. This is very significant. It's not bigger than the alphane speed. It comes in just at the alphane speed. You're still within alphane wave communication with outgoing wind. That doesn't occur by random chance. That's the structure of MHD causality. That whenever you work with the equations, you keep seeing the wave speed showing up. So what we end up with is a current flowing across the field lines at the top of the disk, which is in the slow switch-off shock, and this switches off the toroidal field of the incoming wind. Now, this is a highly dissipative current flow. The plasma comes out relativistically hot, extremely hot, so the synchrotron rate is going to be much higher than even the annihilation rate. So you have lots of synchrotron radiation coming off. Almost all the inertia is being lost to synchrotron radiation immediately. The plasma comes back. The J cross B force, the J perpendicular cross B toroidal, is very strong. It torques the plasma backwards to going minus the speed of light almost, with very large Lorentz factors. It's a very intense interaction. And the energy is highly negative. And so we have, just like in the unipolar inductor, the plasma in the ergospheric disk rotates approximately like that of the field, which is rotating at omega minimum. And this process is transferring rotational inertia from this, that's been imparted to this tenuous plasma by the gravitational field. All that rotational inertia is being converted to Poynting flux. And it's a purely relativistic effect, which I'll show. I have a picture coming up soon, one more view graph. Just talk first about the synchrotron radiation, because this is how we couple to the hole. This is the main source of radiation loss. The plasma is rotating backwards at the speed of light, essentially. So there's this huge headlight effect pointing backwards at the speed of light. So all the photons pretty much synchrotron photons come out along the beam going backwards at the speed of light. They too, you can work out for the photons, they will be negative angular momentum of negative energy. All negative energy trajectories have to go into the hole. They can never escape the ergosphere. So this hot plasma and the synchrotron radiation that's on negative energy trajectories gets absorbed by the hole, extracts the rotational energy of the hole. So let's look at the global energetics of this wind and the accretion disk. The ergospheric disk. Again, to get more details, it's better to look at your own picture than this. This is the last view graph now. So we have an ingoing wind, and here's the top of the disk, and here's the equatorial plane. We have an ingoing wind that has this toroidal magnetic field with it. It gets switched off at the switch-off slow shock by a very dissipative current. That dissipative current heats the plasma to relativistic temperatures and torques it
back to be rotating at negative the speed of light. The synchrotron and annihilation radiation, and therefore, is all beamed on these negative energy trajectories that flow into the hole and therefore extract the energy of the hole. The negative energy going into the hole is equivalent to positive energy coming out. So KE, the out of the hole, through the slow switch-off shock, First it comes out of synchrotron radiation, then to the plasma inertia. Through the slow switch-off shock, it gets converted into Poynting flux, which powers the outgoing wind. So we've established the things we set out to do. We see how the frame dragging affects the twisting of the field and the driving of angular momentum from the ergosphere. And we see how the black hole has actually powered this.
In this situation, it's been simplified because the whole interaction is reduced to the shock layer. We thread the horizon, we don't have that simplicity, and that makes it much more complicated. It's easy to understand.
It's easier to understand dissipation when you hide all the effects in a shock. Okay, so that was going to be the first talk of just establishing the physics of how the ergosphere can drive currents and be a dynamo for the toroidal magnetic field. Yeah. Please. Yeah.
Between the equator and where? And the pole? Well, the pole is on the horizon, so the pole is part of the horizon. I think what you're saying is you have this whole, the ergosphere is a finite volume. I'm looking at like a plane. Well, what happens is that this effect, because of the fact, the way I set up the model, the effect is all going to be in the shock itself. You'll see the effects you're talking about when you look at when the flux tube comes in through the ergosphere into the horizon, you traverse that area, and you won't be able to, there's nothing to bound the flow. So you'll see the interaction in that case will be distributed throughout the ergosphere. But in this particular model, the reason for introducing this model is that it isolates the interaction to a small area that's well defined. Slow switch-off shocks are very well understood. And it's the ability of that plasma to radiate alphane waves is the important thing. What we'll find on the flows that go into the horizon is a similar small region that's the dynamo for the toroidal field. It'll just be suspended. It's going to just be somewhere in the ergosphere, and we'll find that place. So a much more complicated problem is winds from black hole magnetospheres. And the point of this last talk was to really, it actually is astrophysically very important, maybe even more important than this, but originally it was designed so we can understand this much more complicated problem. Now we know there's no unipolar inductor near the horizon, just to repeat this, so we have to find the microphysics that drive currents in this wind. We just can't set up solutions and say, well, it probably works. Forces are that drive the currents and find a solution that's
physics, and we talked about that in the last talk. We showed that. Possibly even remotely relevant effects. One, it can mix the electric and magnetic field in a vacuum that you can't get current closure. In that case, we use that parallel electric field to drive the currents. I showed that on Tuesday. A wheel, or this ergospheric disk plasma. So we want to see how this torsional tug-of-war manifested by this MHD waves is manifested in the black hole magnetosphere. Now, since it gets a lot of popularity, I want to talk about horizon boundary conditions, and they're going to be very different what you normally hear about as horizon boundary conditions. They're not unipolar inductor-like information you normally get. First, the flow goes in relativistically unbounded. This is in the Zamo frames of toroidal velocities, because the 3 velocity goes to -1, the theta and phi velocities die off like the lapse function. All plasma has to co-rotate with the horizon as seen from the stationary frames. This is a very important point. The flow is inertially dominated at the horizon. Gravitational force will win out over any forces you try to impose near the horizon. You can't make any stable equilibria. Just think about what this means. We have a magnetically dominated wind, usually treated as force-free. But near the horizon, the flow is inertially dominated. There's this tremendous transition from being magnetically dominated. And you would not expect that that would happen in a smooth, pretty manner. And it doesn't. So this is a key physical point. Also, we showed on Tuesday that the near horizon space-time will accept any imposed value of the field line angular velocity. I'm going to talk about this more, but the near horizon radiates very negligible magnetic stresses. And this is a new thing that most people don't know about in the literature. You can tell people don't know. It's from the no-hair theorem I proved on Monday that neutral plasma reconnects from any global colloidal magnetic flux advected with the flow. This is particularly important for equatorial accretion.
And this is something that I included in this talk, but there's some pictures that follow that show it. But it's the most common misconception using the membrane paradigm. People just replace the horizon by a conductor. They just pile up magnetic flux right outside the conductor. But the no-hair theorem tells you that those fields will die off, and if you put a whole connection happening, and the way the plasma disconnects from the field. Based on the
No-hair theorem, the hole wants the plasma but doesn't want the magnetic flux. That really won't come into play in this talk, but it is one of the most important results from this. So the basic model we're going to look at is this one. Again, you should look at your chart as your view graph that you have, as this isn't coming out too clear. We imagine that most of the particles, as Finney suggested years ago, is made in a finite region of the flux tube. Because the particle creation zone is heated, and we'll have an accretion wind going into the hole, and we'll look for an outgoing wind going out. So this is an azimuthally symmetric flux tube that's cut in cross-section right here. Now, in order to understand this problem, we are going to elevate the complexity of the analysis beyond perfect MHD, which is not going to be adequate to describe different types of thought problems. So we want a more general situation. We're going to look at dissipative winds and also time-dependent winds. So we're dropping the perfect MHD assumption and time dependence just so we can get more information and look at more different types of thought problems. Well, first of all, and this is the key thing that allows this to be a useful concept, is that I realize that you can still define the field line angular velocity. If we just implicitly define the azimuthal velocity in the ZAMO frames, just the proportionality constant between the colloidal magnetic field and the cross-field electric field, we have a definition of the field line angular velocity implicitly through this relationship relating the ZAMOs to the stationary frame. Well, it doesn't have the same interpretation as perfect MHD. It's not conserved in a flux tube anymore. But it still relates to the voltage drop. This is the important thing. The field line angular velocity is still related to the voltage drop through this equation. The toroidal magnetic field now has a different relation, has an extra term. This is the dynamo. This is the unbalanced EMF term. E2 prime is the electric field perpendicular to the magnetic field in the reference frame of the plasma. This is the quantity that can be surprisingly large and drive very large currents. So this is the important term for the analysis, is what is E2 prime and how does it get generated within the flow. Now, the important thing is we still have this value of omega F related to delta V. And that allows us to look at some very complicated problems, like what the plasma wave speed in a dissipative time-dependent flow, something you normally think you'd be too complicated to write down expressions for. So in the case where we have a finite conductivity and a diffusivity eta, and K is the field-aligned momentum of the wave, we get this expression for the intermediate speed. The point being that when you introduce resistivity into the flow, the intermediate speed slows down. The currents are resisted in their ability to transmit the field. Here's the phase velocity for the fast and slow waves. Also, the fast wave propagation slows down when dissipation starts to set in. And in this equation, we note that when there's a lot of dissipation, the fast wave becomes essentially the sound speed. So let's look at the causal structure. A lot of this is not well known because a lot of what we see is from Blanford and Snajic and Finney. Look at the causal structure for winds, and we allowed for the chance of mild dissipation because we know that can be still part of the coupling process for a small field line angular velocity. In this case, the inner light cylinder is just inside the stationary limit. And so the alphane point is right there as well. But something that's not well known is that the fast point is not near the alphane point. This is a relativistic paired wind. We're assuming the outgoing wind is relativistic as well. There's very little toroidal magnetic field, so if you go back to the expression for the fast speed, it's approximately this. And so the fast speed is actually near the light cylinder in this case. This is not well known. It's usually assumed to be near the hole in all circumstances. And that assumption usually introduces an acausality in the flow. Once you assume that, you've determined everything about the flow, and you can't assume that a priori. Now let's look at relativistic winds where
the field line angular velocity is the order of that of the horizon. The alpha point's still far out in the ergosphere. These are rapidly rotating holes. The fast point, though, now is near the horizon in this case. But this is an important point. I'm reducing some tremendously long calculations into these two statements that are coming up in a very long paper that uses Newman-Penrose formalism in the full MHD equations. They're very complicated calculations, but the result is the following. If you look at outgoing waves emitted from near the horizon, they carry colloidal currents that are primarily perpendicular to the colloidal magnetic field. This is very important for discussing Blandford's Nodžick mechanism, which has field-line currents. Also, if you look at the amount of toroidal field, delta BT over the unperturbed value, from a fast wave emitted from near the horizon in this case, it goes like this expression. F is a well-defined function that's finite, found originally by Hirotani. Alpha F is the lapse function at the fast point, which is very small now because it's near the horizon, and alpha squared is the lapse function where the wave is emitted from. U divided by alpha is the minus U divided by alpha is the Zamo colloidal velocity. By reducing terms, I end up with the alpha on top. It's a little confusing. But the fact that this flow is just ahead of the fast point, this quantity here is negative. That may help you remember what this means. And this is positive down here by definition. So B toroidal is negative, but it's very small. It goes like alpha squared plus this term that goes to zero near the fast point. If you look at the total amount of angular momentum flux in that wave, it dies off like alpha to the fourth at the point the wave is emitted minus alpha at the fast point to the fourth. So there's virtually no magnetic stresses carried by fast waves from near the horizon. And the currents they carry are perpendicular to the magnetic field, not parallel. So let's talk about what the relativistic MHD wave equations mean. They're the combined momentum of Maxwell's equations. And the constants of motion are not determined by the MHD wave equations. The MHD wave equations simply propagate the 5 constants of motion along the MHD wave characteristics as suitably modified by the colloidal velocity of the flow. So given a set of constants, what the MHD wind equations tell you is, with those set of constants, where will the wind propagate to? It's not necessarily going to go to infinity like we want. For most choices of constants, the winds will be failed. Lots of choices. So you don't necessarily get a flow that goes to infinity. You have to integrate it to find out. Now, in wind theory, the wind constants are injected into the wind by the plasma source, and for this magnetically dominated case, by the dynamo for the toroidal field, be the neutron star, the ergospheric disk, and the other problems. So what we're interested in is not the MHD wind equations, but how these constants are injected into the MHD wind. And it's this paired wind problem is very difficult. These are free-floating flux tubes. They're not pinned or anchored to anything, and it's a doubly open-ended flow. There's no boundary conditions to help us. And so here's the general problem, and this is a figure I showed before. Just formally, we have 2 winds coming from our particle creation zone where we have gamma rays making pairs. We have energy and angular momentum flux into the particle creation zone. It's magnetically dominant, so there's very little dissipation. Omega F minus equals omega F plus. It's not relativistically hot, so we ignore the entropy. And the mass flux need not be conserved across this region. So basically, we have these 2 conservation equations. The energy flux in the ingoing wind plus energy flux injected equals energy flux in the outgoing wind, and similarly for the angular momentum flux. But we have these 2 open-ended winds that we have to solve for self-consistently. Now, first of all, let's talk about the outgoing wind solution space topology. There's an X-type critical point at the fast point, and there's 3 types of solutions we're going to look at. The minimum torque solution or critical solution, which it's interesting to know that when you're magnetically dominated, the Poynting flux and angular momentum flux are related by 4 pi over c, so the minimum torque solution is also the minimum energy solution. There's supercritical solutions that have more energy than the minimum energy solution. They still make it out to infinity, they just are not necessarily relativistic. And there's subcritical solutions that don't have enough angular momentum or energy to make it to infinity, and they're failed winds. We'll talk about all 3 types of solutions here, some with respect to the ingoing wind, some respect to the outgoing wind. This is taken from Kennel, Fujimura, and Akamoto. They discovered the critical point structure of outgoing relativistic winds. This is log of radial velocity, and they introduce a very interesting concept. They pick a colloidal coordinate at the azimuthal velocity of the field line. So here's the light cylinder. This is the critical solution here. It goes through the fast point and asymptotes to velocity infinity. So all the acceleration is done pretty much by the light cylinder, or just a little bit beyond it. We've got the alphane point. Here is a solution that has more than the critical value of energy. It reaches this hump, this maximum. Never goes through the fast point as it goes to infinity. But as long as the pressure goes to zero, this is a well-defined solution. You cannot ignore it a priori. Then we have solutions that don't have enough angular momentum. They propagate just past the light cylinder and then can connect to an unphysical solution, which is just a mathematical statement. But in reality, all it means is that it's a failed wind. It can't make it to infinity. So the problem is, how do we determine these wind constants in this open-ended, doubly open-ended problem? We want to know what the field line angular velocity is, equivalently the charge separation that determines the voltage drop across the field lines. And normally this is done by the unipolar inductor. And we don't have one in this case. We have these free-floating field lines. So the plasma injection mechanism has to be important. It may be completely dominant, or other things may enter in as well, other stresses, but it has to be one of the most critical parts of determining the field line angular velocity. And we can see why this is. If you create some pairs on the field line, so the center mass of the pairs has an azimuthal velocity beta phi, and it's different than the field line azimuthal velocity, that creates a Lorentz force. And that drives a current perpendicular to the magnetic field lines, and that current has the purpose of torquing the plasma into co-rotation through this J cross B torque. So torsional stress of the injected plasma can spin up or spin down the field to happen. So now, in order to make progress with these, so far I've just given you
Abstract concepts. And what I want to do is start constructing a model with numbers to illustrate these concepts and also determine different aspects of the flow and see dissipation in the flow and things like that. So I'm going to give a plasma injection scenario. And I'm going to do it for one of the more interesting astrophysical cases where you have a large magnetic field. This is somewhere near the Eddington pressures. The magnetic field is normally used by Thorne and Blandford. The Goldreich-Julian charge density is very small. It's only 1 per cubic centimeter, and that's the local condition for establishing MHD. I use a relation that was given by Finney, where he balanced the pair creation rate to the inflow rate to get the number of pairs created by gamma-gamma collisions. This is 10 to the 8 solar masses, this M sub 8, the units of that. LC is the amount of luminosity above 1 MeV. They look at this equation for a 10 to the 9 solar mass black hole. If you just have 10 to the 41 ergs per second in gamma rays, you'll easily surpass the Goldreich-Julian charge density. The threshold of detection for egret is only 10 to the 46 for a quasar. So the odds are you almost certainly have MHD on these fields. There's no problem making enough pairs. I don't think anyone would have a problem thinking that the gamma ray luminosity in a quasar is 10 to the 41 ergs per second. So just for the sake of argument, I assume the gamma rays are from some type of corona with a typical radius like 10 m, just so I can generate numbers. And the actual numbers don't matter that much, it's the concepts we're after. So this is the way I can make a very crude estimate of the field line angular velocity. And this is a problem that's very worthy of being done numerically and very carefully for different types of disks. It's clear that most of the plasma is going to be made like at radii bigger than 5 m. That's where all the gamma rays and all the flux tube is. And by contrast, there's very little plasma near the horizon that's actually in causal contact with the flow. Sure, you can pile up a lot of plasma near the horizon by the freezing of the flow, but all that plasma, most of it's gone super fast and is causally disconnected. Another thing, we talked about the fast wave down. There's no alphane wave. The alphane point's far out. There's no alphane waves from near the horizon. So all you have is the fast wave, which is very inefficient at transmitting torsional stresses when it's emitted near the horizon. So you have very little plasma that's very inefficient at radiating torsional stresses, plus the rate at which information goes out is redshifted. It's very slow.
So think about what that means. We have this time-dependent local definition of the field line angular velocities defined everywhere on the flux tube. We have a flux tube, and we just have equations I had define the angular velocity of the flux tube. It's not constant. It depends on where you are. So there's actually the concept of a light cylinder exists everywhere. You have a light cylinder in this flux tube. And since the plasma is created from the disk at r equals 10m, you expect the rotating much less than the horizon velocity. So make the horizon velocity when you
First show the plasma in the flux tube. Now this plasma is all within causal contact. You can send alphane waves back and forth and fast waves. It's in total communication with omega F in the flux tube. Because all the plasma outside of like 3-4 m, it's easily communicating with each other. But we've set up a local value of omega F, so there's a light cylinder. And because of those expressions I wrote down, we know the fast point's near the light cylinder and the alphane point's near the light cylinder. So that local flow in a finite region of flux tube is going to go through its fast point and causally disconnect everything that's going on near the horizon. The stuff that's happening near the horizon should play no role in determining how fast this flux tube is going to rotate. And I estimate that for the AGN about 130 omega h for the field line angular velocity. For an isolated Kerr-Newman black hole, a galactic black hole, I did a much more careful calculation. I found 150 omega h. So it's rotating much less. The field lines we expect to be rotating much less than the horizon angular velocity, and that's the situation I want to consider. What's the physics in field lines that rotate much less than the horizon azimuthal velocity? And I'm going to try and unravel that dynamo physics, first through a thought experiment that'll have all the information in it, and then I'll show you a time-stationary solution, and you'll see how all the details of the thought experiment are in that time-stationary solution. So you have an the best way to think about this is the plasma source has established a value of omega F, and it transports it down towards the hole, tries to transport down towards the hole. That's equivalent to it's an alphane wave that's transporting its value of the voltage drop or omega F towards the hole. The interesting physics is what's the alphane wave light that reflects from the black hole magnetosphere, from the ergosphere. That's where the interesting physics is. And so to find what that physics is, you could do this thought experiment. We take some perfectly straight, uncoiled magnetic flux tubes, and we just introduce plasma all at the same angular velocity up here in the flux tube. So this is a pure Newtonian region. There's almost no toroidal magnetic field, maybe a little from the injection mechanism, but it's basically just rotating with just purely mechanical angular momentum. That's what this expression means. Now we release the plasma, let it start flowing towards the horizon, and we immediately see the physics of the torsional tug of war. Here are some inertial currents going across the field lines. And where do they come from? Well, if a plasma in free fall will tend to, if you look at the geodesic, it will tend to rotate faster and faster and faster. The angular velocity will keep increasing to that of the horizon in free fall. Well, here it's stuck on this, it starts at rotating omega F and it's stuck on this rigid field line. The field line's rotating omega F. As the plasma goes down, gravity wants to increase that angular velocity a little bit. The field sits with omega F and it torques the plasma backwards. That's immediately you see the tug of war. The black hole's trying to make the plasma rotate. And so we have the torsional tug of war immediately manifested. We extrapolate this all the way down to near the light cylinder. And you notice the inertial current's growing, and it's very strong near the light cylinder. The reason why, at the light cylinder, it's effectively rotating to all physical observers backwards at the speed of light. So to keep the plasma in approximate co-rotation requires tremendous J cross V forces. It's got to make the plasma rotate relativistically. So look what's happened here. You've generated all this toroidal, all this cross-field current as the plasma is accreted down. You compute Ampere's law. You now have a large toroidal field upstream. This is the reflected alphane wave. The toroidal field is actually so large that it now dominates the injected mechanical inertia. The angular momentum flux is almost purely toroidal field at this point. So this is the essential physics. Down here,
the plasma is in approximate co-rotation with the horizon, so it's being accelerated backwards, faster and faster to the speed of light. I'm going to talk about this in detail, it's very important, but the plasma is going to radiate at that point.
It's going to be highly dissipative because has large proper acceleration. In any event, near this light cylinder, that's where all of our critical points are, and the flow will causally decouple at that point. So we know the toroidal field has to be zero in this region because the toroidal field has to be caused by something. And the only causative agent is MHD waves being radiated upstream. And this is the last point where you can radiate waves upstream. So the toroidal magnetic field will be zero in this region, and all the angular momentum flux is in mechanical form, just at this flow decoupling point. So we'll actually see this type of physics when we look at a time-stationary solution. Well, first of all, there's two possible solutions you can look at. And one is where both winds are perfect MHD. This is the equivalent of the Blandford-Snodgick solution. And the other solution that we'll show is more interesting is where we have the outgoing wind as a minimum torque solution, the solution that extracts the minimum amount of energy from the hole for this particular value of omega F. And this flow has a nice MHD wind going out to infinity, but the ingoing wind is going to dissipate near the inner light cylinder. And it's this dissipation region is where the dynamo for the toroidal field is, just like the switch-off shock was at the top of the ergospheric disc. So let's look a little bit at the Blandford-Snodgick type solution, just to see if we want to consider it as a viable solution. And also because it's very popular. First of all, the Blandford-Snodgick solution has almost no cross-field current anywhere in the flow. It's totally negligible. So the toroidal field is constant from the horizon to infinity. And the toroidal field is solved for by equating the frozen in value of the Poynting flux of the horizon with the same at infinity. And when we do that, we get a supercritical wind. The velocity is very non-relativistic at infinity, about a tenth the speed of light for these low angular velocities of the field lines. It's a totally well-defined solution. There's no reason not to consider it. Now, one thing to consider, we want to look at the causality of this solution. Mathematically, it's fine. The outgoing wind is well-defined. Now we have a non-relativistic outgoing wind. So the inner fast point can actually be near the horizon. You have more toroidal field. We're above the critical value. And so when you look at the expression for the fast point, you have more toroidal field in there. And so this can be near the horizon. But alpha waves can't be radiated upstream, as they can from the Faraday wheel with a connection to a plasma-filled waveguide. And outgoing fast waves are highly redshifted from this region, though. Remember, this is even in the limit that the frequency goes to zero for the fast waves, we still have this relation, even the long wavelength limit, which is what's the significant causal mode. Would always be a long wavelength limit of any of these waves. So what we see then, if we think of the hyperbolic or time-dependent version of the MHD equation, that near the fast points, the appropriate temporal variations cannot be propagated by MHD waves to establish the constants of motion of outgoing wind. Also, and this is the interesting way in which it manifests itself causally. And we have this frozen-in horizon, this frozen-in condition near the horizon, trying to use that as a boundary condition of Blandford-Snodgick. But if you perturb omega F in the plasma injection region, remember I showed this explicitly with Faraday's law, the horizon can never react back to reimpose its value of omega F. It'll never happen. And so the horizon will just passively accept any value of omega F that's been changed. And so this is unstable. If you tried to set up the Blandford-Snodgick solution, you perturbed it, you would immediately go to another solution. So even though the boundary condition is totally valid for the elliptic time-stationary equations, these equations are not physical equations, and they need not be causal. They're just purely mathematical. Another very important aspect of the Blandford-Snodgick solution and the boundary condition is that if you look at the condition that the toroidal magnetic field is constant from the horizon to infinity, it appears that currents are just coming straight from the horizon, field aligned from the horizon to infinity. And we're trying to use the horizon in this solution as a boundary condition. But remember, the only mode of propagation is the fast wave. And fast wave carries toroidal currents that are perpendicular to the magnetic field.
So the structure of MHD waves is totally inconsistent with the Blandford-Znajek mechanism. So we summarize the paired perfect MHD wind solution. The new result, there actually exists a Blandford-Znajek solution for all values of omega f up to the value that Blandford-Znajek give of a half. There's an additional assumption in there. There are two assumptions in their problem. One is the horizon is causative. The second one is that the outflow is going at the speed of light. It doesn't have to go at the speed of light. And when you don't let it go at the speed of light, you can no longer solve for, if that's no longer a boundary condition as well, you can no longer solve for the field line angular velocity. And the method of solution is mathematical and not physical. And the last thing is, very important for considering this solution, is that it's not the minimum torque solution. It's supercritical. It extracts more energy from the hole than the minimum torque solution would. So the interesting case is the following. We look at a case where the outgoing wind is the minimum torque solution in this paired wind system. And what we find is the ingoing wind is a subcritical wind. It doesn't have enough toroidal magnetic field to allow the plasma to get through the light cylinder smoothly. Remember that if it's in co-rotation of the light cylinder, we move it minus the speed of light in the ingoing wind. So the field has to be bent toroidally to allow the plasma to slide forward in the forward direction relative to the field in order to avoid relativistic velocities of the light cylinder. Now, if there's not enough toroidal field, that's going to be impossible. And that's what happens. These solutions are prepared with not enough toroidal field. And the problem is, God bless you, there's no unipolar inductor. This is the essence. This is the reason why we want to talk about the unipolar inductor. The unipolar inductor creates the toroidal field in a relativistic wind. The relativistic wind is just a radiated alphane wave, and from the unipolar light cylinder already built into this wave structure. It has nothing to do with it's just the wave is just emitted and it just keeps going out.
And so how can the field line be bent? The only way it can be bent is by the inertia of the plasma itself. So the plasma is very light. It's the field lines, we don't have enough inertia to do it.
Now let's talk about ingoing subcritical winds. Now the outgoing subcritical wind doesn't make it to infinity. It's just a free expanding flow that'll stall. But there's something different for the ingoing wind, and this is what makes the physics interesting. The ingoing wind doesn't stall because there's a strong force of gravity. Gravity is going to pull that wind in no matter what. It doesn't care if it's perfect MHD or not. It's black hole gravity. It's going to win out over any forces. Plus, the only forces in the problem are J cross B forces. As we'll see, they are also inward directed as well. So all the forces go in, and the plasma is just going to go into the horizon and dissipate, unlike the outgoing wind, which has nothing to pull on it, which will stall and come back to the source. So let's talk about the failure of this wind, how the wind fails near the perfect MHD wind fails near the light cylinder. What I'm going to do is I'm going to try and take the MHD solution, I'm going to integrate it until MHD has to break down. And we'll see how all these effects we saw in the Gedanken experiment turn up. So I need some parameters to the field line angular velocity of the 30th. I assume a magnetically dominated wind through the
sigma parameters of energy of 10 to the 4th. And I'm going to look at the alphane around the alphane point of 45 degrees. The first thing is we know the alphane point is near the inner light cylinder. We can see the effects of this co-rotation near the light cylinder and the relativistic effects already manifesting near the alphane point. So at the alphane point, we're not even moving in that fast. In the Zamo frames, it's 0.2, but we have this huge Lorentz factor, already up to 170 in Lorentz factor, and that's because there's a lot of azimuthal motion due to co-rotation with the field. The field is almost at the light. Intermediate speed is 33.78. The toroidal magnetic field is much less. That's why we're rotating. We're almost in co-rotation here. But it's still interesting. At this point, we're still approximately force-free. It's still a magnetically dominated flow. When we can see this, we really need gamma factors of like 10 to the 4, and we're only at like 10 to the 2 at this point.
So let's take a look at what's happening in the wind, even by the time we've gotten to the alphane point. And this has both solutions on it. And again, it's probably better to look at your version than what's here. Now this axis is accurate. This is the poloidal velocity in the ZAMO frame, the tree velocity. This is just a proper distance along a flux tube, and it's expanded and contracted in different areas for visual. So here's the horizon, here's the inner light cylinder, here's the outer light cylinder. Here's our particle creation zone. Here's our initial data, I plus and I minus, for the two winds. Here's the perfect MHD wind called the minimum dissipation solution. See, it goes through the alphane point but never goes through the fast point. I arbitrarily chose the shape of the magnetic field to follow Kennel's calculation. Here's the other wind, where the outgoing wind is the minimum torque solution. It goes through the fast point. And now the ingoing wind is the one of interest. It's this piece right here. First, it looks just like the minimum dissipation solution for a while, but then it has to start co-rotating with the field. And here's the alphane point, for instance. And what happens is we're going to be able to integrate the flow all the way to here, and then we're going to find that MHD will actually break down. So we're going to do this idealized integration. Assume MHD holds, there's no radiation, just force the flow as far as it can go. And notice what's happening. The colloidal velocity is decreasing. In the other solution, it gets accelerated by the black hole. And the reason why it decreases is that you have so much azimuthal motion from co-rotating with the field, and beta squared always has to be less than or equal to 1, so there's just nothing left for beta poloidal. U poloidal, though, keeps going up. The 4 velocity will go up in the poloidal direction. What we're going to find, though, is there's going to be an extension of this solution inward, a dissipative solution, and it'll come in about right here, and that allows you to go through the fast point and proceed on towards the horizon. Where's it, the ergospheric boundary? It's right here. It's just right outside the light. It'd be like right there. So all this is happening just as you enter the ergosphere. As soon as you enter. And you think, oh, well, we should wait longer till drastic effects happen, but the fact that the ergosphere can impose a positive angular velocity on all plasma over there tells you there's very strong forces of frame dragging at work, even just at the stationary limit. So I'm trying to push this MHD integration all the way to the end, and I find that I can go as far as this value, just past the light cylinder. The poloidal velocity keeps slowing down. The azimuthal velocity becomes 99.37 that of the speed of light. I get a large Lorentz factor. The force-free condition is broken down at this point, but it's still more magnetic than inertial. And we find, if we compute the invariant F mu, that it has changed sign at this point. The field has gone from magnetic to electric, and MHD is broken down. But the flow still is going to proceed inward. This is the important point. We can compute we'll call it the final surface where this MHD flow would end. Call it this final surface. We put an observer on there like the ZAMOs that's sitting at that constant radius and compute gravity. It's huge, 0.76 over m in geometrized units. Plus, remember, there's lots of, in order to enforce co-rotation near the light cylinder, there's a lot of cross-field current, a lot of inertial current. Well, that J cross B force is also inward. Plus, the flow is already moving at 1/10 of the speed of light inward, so there's no reason in the world why the flow is going to keep going in. All the forces pull inward. And what this is in terms of MHD is the gravity is acting like a rarefaction piston that's pulling the plasma across the magnetic field lines. Now, the most important aspect of this study is this equation over here. This describes all the physics of how the dissipation occurs. And it's a very difficult equation to get, but let me motivate it, and we'll talk about its implication. Near the light cylinder, we've given a lot of relativistic inertia to the plasma, and it's rotating at almost the speed of light backwards. And we're going to find a radiative instability due to this effect. And the question is, this is related to the point that you would think, when I first thought of this, rotate almost at the speed of light. And the plasma, you could always make the inertia
as big as you want. the speed of light in rotation, minus the speed of light. Why can't the plasma just rotate and almost minus the speed of light and just bend the field smooth flow with mild dissipation? And so that's the question. Why can't you just rotate backwards and almost the speed of light and create the toroidal field that's needed to get the flow? To solve this problem, how does a magnetically dominated flow accrete onto the horizon? And the reason is because there's a radiative instability. The only place where the Lorentz factor really increases substantially is when you're right at the light cylinder. You know, if it's you're 99% the speed of light, you don't have much of a Lorentz factor. You have to be 0.9999999 or something like that to really get that exact number you need to get enough inertia. And so all this happens over very small proper distances. And so there's huge proper accelerations as the plasma comes into co-rotation near the light cylinder. And remember, the plasma is rotating backwards at the speed of light. So the radiation that comes off is also beamed backwards on trajectories that are going against black hole rotation. And so they're of negative angular momentum. And this exacerbates the problem. The plasma essentially has too much positive angular momentum. It needs to be torqued backwards to rotate with the field. If it radiates negative angular momentum away, that's being imparted to it by J cross B forces, the situation's even worse. It's even farther from co-rotation. And that's the physics behind the instability. Now, the instability I'm talking about is for the proper cross-field electric field. This is the field that drives currents perpendicular to the magnetic field. Delta M is a perturbation from perfect MHD. This is you take the MHD value of angular momentum and you mechanical angular momentum and perturb it. So in perfect MHD, this term is 0. This is the photon angular momentum flux, KL, and the unperturbed value is 0. Perfect MHD plasma doesn't radiate, and so this is the amount of radiated angular momentum flux. And it's a very long calculation to get to this point, but you see all the causal structure in here. You see the sound, slow, and fast speed showing up. Now, away from the fast point, ahead of the fast point, this term always dominates. Notice when you get near the fast point, this term can be very small compared to this term. And this makes for the instability, because then whenever you start driving a proper electric field, you start radiating away negative angular momentum, pulling yourself farther from the co-rotation frame of the field and increasing the proper electric field. And so this is the dynamo term right there. This drives everything. That's where the physics is. So in order to find out about that point, where that's happening, we find the fast point in that perfect MHD flow. This unstable growth of E2 prime will occur. Where the dynamo happens and the fast point is there, that's where the causal decoupling will happen. So it turns out the fast point is given by these parameters. The fast speed is 187 C. And we expect that this dynamo is going to occur in a very small region because you're near the light cylinder, near the fast point anyway. Remember, dissipation makes the fast speed even slower. So once it starts to dissipate, it'll almost immediately causally decouple. So this is almost like a thin surface layer type of a thing. Now, they will appear to just grow without bound unless it's quenched by some kind of resistivity. And the resistivity is supplied by streaming instabilities and particle trapping in the potential well through the bunching of the plasma. So the bulk kinetic energy you normally have from driving the current with this E2 prime turns into thermal energy in these wells. So there's very strong dissipation as the flow decouples. So the energetics of this whole flow is the following. We have a reflected Alfvén wave from the plasma source. And there's an analogy to this in classical physics. This would be like an Alfvén wave that's reflected off the magnetosphere in the ergosphere plays a role of a lossy conductor that's rotating. And a similar problem was done by Zoldovich in '72 where he wave was amplified. This is the same, essentially a lot of the same physics that's here, but electromagnetic. The plasma is near the fast point, rotates spheric disk. It's highly distant. The radiation from this dynamo by the head-like effect beamed on these negative energy trajectories that happen to the plasma, and all the radiation ultimately spin down the hole. just like the ergosphere. So let's look at the global energetics in a picture here. So here's the outgoing wind up here, the paracreation region. We see an ingoing wind coming in. We have a little bit of inertial current here, and then we get a lot more inertial current as we get near the light cylinder, and co-rotation is trying to be enforced. And that's where all of our critical points are, and the causal decoupling is. So this is the dynamo region, and it radiates a lot. It's the plasma's on negative energy trajectories, the radiation's on negative energy trajectories. Negative energy going into the hole is equivalent to positive energy coming out. So effectively, the rotational energy of the hole is powering giving relativistic inertia to the plasma, which through this dissipation layer is converted into Poynting flux. Now, we want to also comment on the wind below this region, which is causally decoupled. But this instability persists all the way to the flow. MHD will never be restored. So any MHD boundary conditions at the horizons are totally irrelevant. This is going to be a non-MHD flow, and the reason why, look at the direction the current's flowing. It's making the toroidal field more and more positive. And it's making the possibility of co-rotation more and more difficult all the way down. And I describe it in a paper what this flow is like. It's a very energetic dissipative flow, but we don't care what's going on in the flow because it's all causally decoupled. All this stuff goes into the horizon, and the essential physics is all out here. Although this, from a physical point of view, it's fun to play around with all the bizarre physics that goes in on the dissipative flow, but astrophysically it's uninteresting. So I'm going to go down to the last view graph here, put a perspective on the paired ingoing dissipative wind solution. We had the perfect MHD solution also, remember, the paired perfect MHD wind. By contrast, this wind extracts the minimum amount of momentum and energy from the black hole for a given value of omega F. A good reason to consider it. We know the microphysics that drives the currents. There's a known causal microphysics for current generation, and it's totally consistent with the nature of black hole gravity and MHD waves. This is also, turns out, very interesting. This is the true minimum dissipation solution due to the second law of black hole thermodynamics, that energy lost into the hole is equivalent to entropy generation in the horizon. Thus, the minimum torque solution is equivalent to the minimum dissipation solution, just as it is in the MHD pulsar. Surprisingly, it's not the perfect MHD solution. General relativistically, the minimum dissipation wind with ingoing deflagration, this ingoing burning wind, and outgoing perfect MHD wind. So in all three counts, it makes sense as the physical solution. Are there any questions? Yeah? To be what? That's the energy it's the negative energy that was absorbed. It's the rotational energy. Yeah. And the mass goes up, and when the mass goes up, that's the entropy increase. No, it doesn't mean that. It means that the rotational energy is taken out from the black hole. The black hole is spun down, the mass and the surface area of the horizon go up. Yeah, in terms of the thermodynamics, that's what happens, yeah. Sorry to torture you with all that, and it's very compact, talks of lots of stuff in it. Are there any other questions?
Of the efficiency of the extraction? Mhm. Yeah, I should say the extracting rotational energy. I think I may have left a word out of here. I think, and I could be wrong, 'cause it's been a while since I looked at this. It's a good point. If you look at the whole point of the membrane paradigm, and I was maybe referencing it too closely, was that you look at the dissipation of the Poynting flux on the horizon. And Thorne equated that to an entropy generation on the horizon, just like with the entropy generation in a unipolar inductor. I don't know if that's done right or not. I assumed it was. I don't know. I thought that if you just slow down the hole, doesn't the surface area go up of the hole and therefore the entropy? What you do, I guess the way to say it is you increase the energy, actually, of the hole. You put some non-rotational and irreducible mass into the hole and take reducible mass away. But the overall mass increases. The energy of the hole actually goes up in the process. It's less rotational energy, but the energy of the hole actually goes up, right? You've been looking at the Blandford-Genodjic solution. Is that what happens? Does the entropy stay constant in that case? Well, I don't know if I'm supposed to respond to this or not. Well, maybe we should talk about that afterwards, the entropy of the horizon. Because it is technical. There must be like a Penrose.
Yes, but you have to keep your vacuum constant. Otherwise, you are just doing all the work in order to keep the mass. And that means that you are not extracting energy to infinity. This is exactly the big difficulty in extracting rotational energy, extracting. Because if you increase the area of the black hole, all that energy is not extracted.
So what's going on here? Part of the negative extraction into the hole. What's the final state of the black hole?
It depends how this is the reason why I showed this effect in the beginning of the meeting, the energy potential. It depends from the energy and the momentum how they are tuned in order to keep the surface area constant. If you don't keep the surface area constant, then all the energy you are transferring just goes increasing the level of the
Well, how can we put it just in a general concept? How can a negative energy particle fall into the horizon and not decrease the energy of the black hole? I think what you're thinking about is rotating backwards, you don't necessarily extract energy. The forward velocity actually is negative energy that we have. So we're taking into account, when solving the full forward velocity, I think you want to imagine that
It's important to think about the reversible and reversible transformation. I mean, there is only a little bit far and set from transformation. The one going absorbed near the right, which they are the best. And these ones are the ones that they don't increase the mass of the black hole. But it's really crucial.
well, that, as part of that depends on the fact you're splitting a particle in half in that discussion. Yeah, it seems to me it's inescapable conclusion that a particle is negative. That's all that exists in the whole universe outside the black hole is one particle. Negative energy projected is fine. That seems like I would have to do it.
Okay, let's pick.
I need that particular machine.
Will be the Chakrabarti. He's going to talk about the global solution of the reaction.
No. I already talked about the reactor, I think.
So this will be
I need this particular machine if you can do that, okay? Actually, the pictures don't come quite all right. Well, I'll come back to it towards the end, but by this internet in the air itself. So, could you kindly? No? No, somehow he does not know. Up. Okay. Well, I am going to talk about some work on accretion processes onto black holes and some of the consequences of the so I'll need that. Okay. Some non-conventional kind of disks we will be discussing today. Namely, they are not mostly not Keplerian disks. We will try to prove that the matter when they come close to the black hole, they don't remain Keplerian. So I want to go back to a little bit of historical part of this thing. My interest in this topic. When I was a student in Chicago, again, you know, I had in mind this following problem, that when matter is falling onto a black hole, or it is coming out as jets, they are following exactly same set of equations. So why not both the solutions be derivable from the same set of equations, probably two different parameter space. In fact, I wrote a couple of papers in 1984 showing that if you take the flow in a full general relativity in card geometry, you take the flow purely rotating, okay, and you assume that the angular momentum distribution is that of a power law distribution, then power law is not with respect to the radial distance but with respect to a von Zeipel cylinder. And von Zeipel cylinders are the geometric cylinders which behave like radial distance at infinity. So you take the power law, you can integrate the equation exactly, the Euler's equation, and when you want to satisfy that equation, the quantities to be finite on the equatorial plane, you produce thick accretion disks, and when you the same solution you take and make sure that it is regular on the axis, you get a pre-jet solution from the same set of equations. So here you have the power law C lambda to the power n. When there is large C but small n, you get disk-like solution. When you have small c but large n, you get the jet-like solution. So, but that time, of course, it was fashionable to do thick accretion disks which were not really having any radial motion. So ultimately, the jets were the radial motions were added to the jets, and the transonic flows in curved black hole geometry. It came in an astrophysical journal in '86. But do this entire radial motion thing around the black hole
even for the accretion. So you remove the condition that the constraint that the matter is the radial motion also, and try to see how the solutions look like. Now, when you add this advection, when you add this radial velocity, so to speak, you see that there are some fundamental things you have to satisfy. First of all, if you solve the equations exactly again, you find that v is equal to 1, namely velocity of light, but the sound speed is never that high. Sound speed is at the most c over square root of 3 with the steepest equation of state, okay. So the Mach number on the horizon has to be always larger than 1. In other words, matter must be supersonic when it is entering into a black hole. On the other hand, very far away where the flow is Keplerian, we know that the flow is subsonic, Mach number is less than 1. So clearly a subsonic flow is coming towards the black hole, and on the horizon it has to be supersonic. So at some point it has to pass through a sonic. Black hole accretion solutions must be fundamentally transonic. They have to pass through a sonic point, at least one sonic point. And again, there is a theorem, I don't have, yes, I can, that if the flow passes through a sonic point, you just calculate the sound speed at the sonic point, and sound speed square will be greater than 0 only if the angular momentum of the flow is less than the Keplerian angular momentum. So in a black hole accretion is not only transonic, it must be sub-Keplerian or Keplerian disk.
It must deviate from a Keplerian disk and deviate in to become sub-Keplerian before it enters into a black hole. The opposite situation is not correct. If you consider a neutron star which is rotating slower compared to a Keplerian flow, a Keplerian rotation, the flow has to be sub-Keplerian to match with the boundary condition. At the same time, since the matter is hitting the surface, it has to be subsonic also. So it is subsonic sub-Keplerian on a neutron star. On a black hole, it must be supersonic sub-Keplerian. Sorry?
Why you have this condition? Because the particle cannot have a stable orbit all the way to the horizon?
Yes, it has to, yes. And the radial velocity has to be velocity of light, the v equals to 1 in order to keep the specific energy finite.
But if you take an orbit around the Tesla co-rotating, you have an orbit stable all the way to the horizon.
If it is extremely rotating, a equals to 1. If a equals to 1, then only the marginally stable orbit matches with the horizon. Yes. No, actually if you don't have the, let us say not extremal, but if you have even 0.999, there is always a scope that you have to enter through the horizon with the velocity of light, so you have to become supersonic. Only if a equals to 1, you arrive. But we know that we don't reach that particular, somehow Kip Thorne told us there is no more than 0.998 or something. So the next point is that when matter is coming towards the black hole, it doesn't have much time to lose angular momentum. It is coming so fast, the angular momentum remains almost constant, and the centrifugal force, which is L square by R cube, is going much faster, is going up much faster compared to the gravitational force, which is going like 1 over R square. So centrifugal force starts dominating, and at the same time the gravity is pulling, but centrifugal force starts dominating, and so you have something called centrifugal barrier just outside the horizon. So even if matter is being pulled, it is slowed down because of the centrifugal force, and this centrifugal force is not negligible, and this is true only because angular momentum is not Keplerian. If the angular momentum were Keplerian, then L square goes like R over R cube goes like 1 over R square, and that would balance with the gravity. But since viscosity doesn't have much time to transport angular momentum, the L square by R cube starts dominating, and therefore the centrifugal force starts dominating, and black holes and the matter slows down, and the black hole also has something called a boundary layer. I will come to this in detail. But